All right, back with second session on our user group here tonight. We had just gotten done talking about assembly or sketch tips and tricks, and kind of rabbit trailed here and there a little bit, just as I promised I would. That's easy to predict. We're going to talk about assembly tips and tricks. So again, we'll start theoretical here on the PowerPoint presentation. Oh, same stock slide about me. I don't know that I need to go over that. All right, same stock slide to universal CAD rules. Everything will break, everything will change, everything will break. Overarching, whatever I wrote, assembly rules. Everything should be fully defined, nothing fixed. Now, a lot of what I see is the first component in your assembly has a little F by it. It has the F by it because that's what SolidWorks does by default. And of course, that's what SolidWorks does by default, so it must be okay. Right? Except there's like 30 other SolidWorks defaults that we all hate and curse at. So the number one thing that I try to preach and communicate is do not let anything ever be fixed. And the reason being is if you have a fixed component in your assembly, where is it? Nobody knows. Right where you fix it, right? But from an intentionality standpoint, where is it? Nobody knows. It's just there. Now, it might be on the origin. If you click the little green checkbox instead of in the graphics view, it might not be. And with a mate constraining the base component, it's in a known place and you can edit it and move it. So one of the biggest problems if something is fixed and you float it, you don't know where it was in geometric space. So if you move it, you don't know how much you moved it. If you want to move something over 1/4 of an inch from a fixed point, and it's not in the origin or it's not constrained in some way, you're totally SOL, which is a problem. Or there's a bunch of workarounds, but. The other thing is to work off symmetry. Again, origin being center mass. Using those guaranteed 3 planes to the best of your abilities. Build intelligence into your assembly structure. So general principles, same group of components can be used in more than one place. Make it a subassembly. That's really obvious. Most people understand that. That doesn't usually take much debate. If there are items that are logically assembled, make a subassembly. So I'm going to put these 10 things together all the time consistently on the bench, and then I'm going to put it in the machine or something. Sub plates and that kind of thing. If there are too many items, if you're trying to make a detail print and you realize you're sectioning it 3 times and doing 10 balloons and then doing a detail view and a break view and a whole bunch of stuff just to try to communicate what it is on the print, you probably have too many parts in your subassembly. Possibly make more. And then there's a point of diminishing returns, but there's substantial performance gains to be had making subassemblies. And the reason is because every single live mate that SolidWorks has to calculate is a performance drain. And in a subassembly, SolidWorks calculates, let's say, 100 live mates, which would be roughly 33 parts. And once those are calculated, that subassembly is a blob that goes into a parent level assembly. That blob only then needs 3 mates to constrain it. So you've got your chain of mate dependencies, and at every level, SolidWorks is going to calculate the mates once, and then a second time if a change is made. So at the top level, if you have 10,000 mates versus 10 subassemblies with 1,000 mate each, and you make a change at the top level, SolidWorks is going to live calculate 10,000 mate solving. If you have 10 1,000 part assemblies, and you have those 10 assemblies at the top level, you only have 30 mates, and you change a mate, you are only calculating 30 mates. And you open up one of those subassemblies as 1,000 mates, and you make a change, you're calculating 1,000 mates, never 10,000 at one time. I've seen assembly load and assembly rebuild performances drop in half by adding subassemblies at the extreme end. And there's a point of diminishing returns all around. But so there's your subassembly general guidelines, and that's just you just got to figure it out. There's not a universal rule there. More overarching assembly rules continued. Mates are performance hogs. Avoid them when possible. We love patterns, and there's a few listed there. We love mirror, MultiMate, etc., etc. And I'm going to pull up a bunch of sample models that I prepared here. We'll work on the table a little bit more too. When mating, select the most reliable geometry. So in order of decreasing reliability, what can never ever change? Planes. If I can reasonably use planes in a good design intent environment that will accomplish my goal, there is nothing more reliable, period. Secondarily is faces. Because faces are the most reliable object. If I have a face and I chamfer the edge of that face still exists. if the next less reliable is edges, and edges where two faces connect. So if either one of those faces change, there's a chance that edge will fail. Or if I chamfer the edge or change the edge disappears. And then in increasingly order yet, we have points. Points are two or more edges connecting. So you can see the compounded variance of our liabilities. So we're going to limit our liability and say what possibly, when something changes, what possibly can go wrong. The odds of something being mated to a point is the highest odds of something going wrong. Because any face change that affects an edge that affects a point, you're screwed. Secondarily, edges. Third, faces. Predominantly, planes are your most reliable all the time, hands down. Configurations can be helpful. It depends on the environment. It depends on the client. It depends on the machine or the design. Sometimes I'm configuration gung-ho, and sometimes I say they're going to burn you, don't use them. It's kind of a crapshoot from a rule-based standpoint. It's totally variable based on the environment. But they're awesome for showing kinematic motion, but it's a performance killer in a flexible subassembly environment. Showing alternative positions like open, close is fantastic. People who insist on putting hardware in their models usually will put all their hardware in a folder and configure it so it's a lightweight model that I can actually use, and then I switch it back to hardware, which I can't use because it slows down so much. So there's those options as well. And we're not going to talk about external relationships yet. I'm not sure we're even going to get to in this presentation because that's a long story to talk about, or a lot of data to talk about. All right, so first example. On my desktop, I've got example. So here's the first example of configurations being helpful. I have a Destaco clamp. I want to make sure my Destaco clamp is actually touching my part. I also need to make sure it removes enough so I can get my part out. So I have a closed configuration and open configuration. Here it's open. Look at the top. I can take my part out. Here it's closed.
Can you give me a nutshell definition of what a configuration is?
Not in an hour.
Oh, really? Okay.
How long do I lecture about configurations before I actually touch it in class for those students that are in the room? probably an hour and a half. The easiest nutshell is, if you've ever heard of like Schrodinger's cat. Okay. That nutshell wasn't easy. So the theory, so Schrodinger was a. Kevin, you know?
The easiest way I can think of to put it is it allows you to change things based on context. So you can change mates, you can change positions on things, you can change colors, you can change display states. All kind of the same stuff that's already in your assembly.
Yeah, it's a part or an assembly. It's a component with a split personality. So Schrodinger's cat theorized that if you put poison in a box, put poison on the table, and you put a cat by the poison, you put a cardboard box over the cat. It could be theorized that the cat is both dead or alive until you open the cardboard or lift off the cardboard box and see if it ate the poison or not. So in the same point in time, you theoretically can theorize that it's both things. SolidWorks can do that multiple times over. So at the exact same time, and maybe I just have a sick and twisted mind, and that's the best example I have, but at the exact same time, this assembly, which is a single part or single assembly file on the server, consisting of multiple components, which are parts, the identical time this one document is simultaneously open and closed. And you can do this 1,000 times over. It's super powerful, and people think it's really cool, nifty toy, and then they use it too much, and then it all blows apart, and then they don't think it's very cool anymore. It's got mixed reviews, we'll put it that way.
So it's a tool that you're using in assembly?
Or a part.
Okay.
Yep. I don't know if I have any good part examples pulled up right now, but we'll get there. So configurations are cool, but notice where my origin is. In this particular instance, it is constrained around the nut driver that I'm driving, because that's the centric of my particular design. But I've at least got my right axis or my right plane. And so if we start looking at some of these mates, the very first mate, we'll get rid of all this. The very Oh, yeah, I forgot about that. We'll get rid of those two. So the very first mate here is an origin mate coincident with aligned axes. So I put in my part, which was automatically fixed by SolidWorks default, right click on it, float. And then I picked the origin of my part, my base part, the origin of my assembly, coincident and align axes. So now my part is fully constrained with a single mate. Most of the time we need 2 or 3 mates. You have to constrain an object X, Y, and Z. But when you want an object exactly on the origin of the assembly, you can do a single mate of the origin's align axes, and one mate will constrain that. So back to our PowerPoint. Mates are performance hogs. If I can do something with 1 mate instead of 3, 1 mate is better. Not only from a liability standpoint, one thing to break, one thing to fix, but from a performance standpoint. Moving on. Yeah, we'll do this.
You put the axis of your planes on the origin, is that what you just said?
So the option is align axes. It should say align planes because there are no axes to align. It's one of those really frustrating SolidWorks nomenclature things. But it's basically aligning the right plane to the right, the front to the front, and the top to the top. If you uncheck that, well, my model's going to blow up now, but if you uncheck that, this is, If you uncheck that, it's like a ball and socket joint, right? It can rotate because you just touched those two origins. But if you align axes, then it's going to be constrained to that origin, as if you did 3 individual mates, right to right, front to front, and top to top. So the other thing is here, there's no way that I was going to mate 2 handles in place. I have one handle, it's in its position, and I guess I patterned that as well. I have one handle, it's in its position. I have the right plane down the center of my design because it's good design intent, right? This only works if the origin's in the middle of or where you logically want your part to be. It's not exactly middle in this instance. If my origin was in the bottom left-hand corner and I made it my origins, this wouldn't work. So I can limit my liability throughout the design by having the origin in the middle and mirroring about that center plane that I got for free. I could always go and create another plane, but then I'm increasing my liability to decrease my liability. And then we also have another awesome feature that I don't know, for some odd reason, it's not very popular. Not a lot of people know about it. But I'll suppress this feature again. I can't, so here's a bushing. I can't mirror my bushing very well because I don't really have a good plane, and then this bushing hole is not mirrorable, right? It's some random spacing that's idiot-proof, so you can't put this on backwards. So the design has been idiot-proofed, which makes an odd pattern that isn't mirrorable or like a linear pattern. So SolidWorks has a pattern feature called, and this always flips me up, but it's pattern-driven component pattern, and no, I won't repeat that. And basically what it says is there's a series of inputs that you can give it. In this instance, what the bushing was that I wanted to pattern, and what the pattern driving feature component is. And where this came from was my hole wizard. So the hole wizard for this particular hole has these 3 points. And so if I put a single object in any one of those 3 points, I can pattern and say, fill those other points. This is fantastic for bolt hole patterns, if you're trying to put something in it, or like if you, I have a third example that's really stellar for this. I think it's this one. Yes. These are just all random fixtures and machines and stuff that I've designed over the years. So if we look at something like, wait for it. So look at something like this. I had to prove to the customer that they could hold 40 of these parts in queue before they went through the machine. So these are all patterns. Now they're not linear patterns because we've got the curve at the end, but I put the first part in there, drew my line, and said make this part go along that line in instances of this, and I get my pattern. Right? It would be absolutely ludicrous to mate that many times, or it would be huge performance implications and a lot of time. And same thing with this. So I'm going around the curve, straight around the curve and up, and just this is how many I want. So there's a lot of pattern options that will save a lot of time if you know that they're there and how to use them. This is another example. All of these here, every single one of these posts all follow a common bolt hole pattern, or all follow a common hole wizard feature, is what I meant to say. And I think it's here. Been a while since I've been in this design, so I don't necessarily know it. Yeah, so those are just pseudo randomly spaced holes, right? And a lot of people think they're really smart with themselves using copy with mates and then like click, 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 click. And you get an instance of the component and 2 or 3 mates copied multiple times. But in this instance, I can do a magical component-driven pattern, or pattern-driven component pattern, whatever that's called. And so I picked all 3 of these, the spacer, the component, and the spacer, because there's multiple pieces of steel here. Picked that whole pattern, which we can see highlighted in blue here, and patterned it all around.
Where'd you pick the whole pattern? How do you...
Just through the graphics view.
I'll just pick one of them?
Pick.
Okay.
Now, sometimes it's not aligned, so sometimes you get a pattern that looks like that, because SolidWorks knows the geometric pattern but doesn't know where the starting point is. So you just have to click, select your seed feature, grab your seed feature, and the pattern will realign. But I'm placing, I don't know how many, 40 parts, and it builds nearly instantaneously.
So it doesn't use in the background mates to create the pattern?
No.
Okay.
So we've got that going for us, which is super cool, right? The other thing is I have a lot of things mated to this face. I've got all these guided pneumatic cylinders and a handful of other things. So every single time SolidWorks in mating, we're trying to get 2 faces to touch, SolidWorks has to go through the CAD model, find the face with that ID, and say this face and this CAD model of this orthographic orientation has to be coincident and match this other face with this other CAD model and stick them together. Every single mate, every single time. Now, as amazing as the software is, it does it as fast as it does. But mates are performance hogs. We want to minimize them when and where possible. So here we can see that there's these cool little paperclip mates with a lightning bolt, which is a folder that has a bunch of submates. And what you can do is you can do a multi-mate. Is this the one I wanted? This is the one I wanted. You can do a multi-mate. And so in the context of coincident here, or you can do perpendicular, parallel, etc., you can say, here's one face, and then all of these faces, we want to touch that one face. So you can see the purple highlights here, all the various pneumatic cylinders, and then I think there's that one up there. So I took whatever that is, 5, 6. I took 5 or 6 mates and made it one mate. And the computational efforts are cut in half for everything after the first subsequent mate. So the very first mate, SolidWorks has to find 2 faces and make sure they stick. Every mate after that, it knows where this face is. It just finds this one, and that one, and that one, and that one, and that one. So this is the multi-mate feature with the Create Multi-Mate folder checkbox. If you don't check this box, you don't get that result. Box is really important. It's grayed out now because it's checked. You can't uncheck it. But when you go to make the mate feature originally, you have to make sure that box is checked. So you have your single face, your common reference, and then your all the objects you want to mate to it. And the computational intensity will be dropping in half after the first mate, because the first mate is still 2. Then after every one of that, it shares that. So this is the flexible subassemblies. So I have a pneumatic cylinder here. Oh, I got ahead of myself. I want to talk about purchase components. This is another great performance and liability limiting feature. So we've all downloaded purchase components to Stego clamps in this example, pneumatic cylinders, etc., etc. And they give us really, really annoying files. That pneumatic cylinder, I think, was like 7 files, right? I need 2. What 2 do I want? Cylinder, rod. Okay? So I need to store 2 part files on my hard drive and then store 1 assembly file on my hard drive. That assembly file has to know where those 2 or 7, in this instance, 8, whatever it is, part files are. It has to load all those 8 part files, load that assembly file, put those 8 part files in the assembly file, and constrain them in 3D space, and then you get your assembly. Now, again, SolidWorks is amazing at what it does, and it does it nearly instantaneously, but in an extrapolated view, that's a lot of work. So, new thing, I think SolidWorks 2015 or something, they came out with this. But what you're able to do is, oops, we'll do it over here, is you can click on parts. You can click on any part in any assembly and an assembly. So it's any component in any assembly. You can right click on it and you can say make virtual. If I can find the button. Thank you. Make virtual. What make virtual will do is it'll turn the assembly into basically a giant zip file. It'll take all of the parts and embed them in the assembly. You can delete the part files off your hard drive. And I'll demonstrate that accordingly. This file is stored here. And the file name is this. All right. I actually don't know if this is going to work. We'll find out. If I hit the delete key, Windows is going to tell me this file is being used. It's in that assembly. You can't delete it. Close SolidWorks, try again. Right? We all understand that. It's a file that's in use. However, if I go like this and I say make virtual, it'll warn me. I say yes. It does a little thinky bit. And then it copies that part file and puts it inside of the assembly. If we go back to here, the component is component at assembly. So here's my assembly, Destaco 650. So this is the component inside of the assembly. There's no $, anything. It's inside of the assembly. Which means if I go back to here and I try again, okay, well, Windows is still retaining ownership of that. But if I close SolidWorks and reopen this, this file is no longer needed. I can delete it. Which means if I do a save as of this assembly and dump it somewhere, or let's do it this way. Let's do a file, pack and go. Everybody knows what pack and go does, right? And I browse into my desktop and I say test, and I select this folder and I pack and go all of this to that folder. How many files will I have in that folder? 1. That one assembly file has all 7 files embedded inside of it. It's like a zip file for SolidWorks. All the information is still there. Now this is very, very, very dangerous for anything but a purchase component in which the files are just necessary evil, right? This file on my hard drive does me 0 good. I'm never going to put it in another assembly. I don't care. The only thing I possibly care about is this assembly and these 2 configurations. So this will again limit my liability. We've all opened a pneumatic cylinder and it blows up because that rod got renamed, got deleted, got moved, isn't there, or whatever. Right? I can take all those files, suck them into the assembly. Now you cannot delete this part because that part does not exist outside of the assembly. It's also more performant because it's easier to open one slightly larger file than 8 smaller files. So the virtual components are fantastic for purchase commodities in instances in which we do not need the components. And that's what I did here. So this assembly here contains all of those parts. So I only have a single file on my hard drive that I'm managing. So back to...
So do those virtual parts end up in bill of material?
Yes. They are every bit of a part of a part. So I can still open the part. I still have properties for that part. The only thing you can't do is make a drawing of the part because the drawing needs to have a physical file on your hard drive to look at.
So can you exclude it from the bill?
Yes. Yep, or in this particular instance,
Just like any
yep, it's identical. In this particular instance, I just said, oh, I'm in a part, duh. In this particular instance, for that particular assembly, the bill of material properties are hide, so the children never show up. Remember, the assembly is a part, so the parts are just geometric references. But, yeah. So that's an assembly with no part files on the hard drive. They're all embedded in the assembly, much faster, less liability, less to break, less to go wrong. Very easy to do. And then I also made this particular assembly flexible in the context of this parent assembly. So if I rotate this part, that assembly, and you can see how chunky this is because, wait for it. Second to the bottom. When necessary, they can be flexible to show kinematic motion. That's supposed to be to show kinematic motion. but it's a performance killer. So we don't like to do it, but it is possible. It makes for a pretty picture when you're doing a design review and the customer can't visualize how the roller is going to end up down the good part chute. And you're like, okay, click, flexible, and the customer's like, oh yeah, that's cool, right? That's the goal. So we've got patterns, eliminate mates, MultiMate to eliminate mates, make virtual to eliminate unnecessary components on the hard drive and make SolidWorks faster and more reliable. What else is, our mating, we like planes. Okay, so go back to our planes here. If I look at my right plane, straight down the center, where it should be, right? Center mass, center origin. And if I look at my mates, I have a right plane mates. So here again is a MultiMate. I said the right plane, my common reference is the plane of my assembly. And now I have 4 more references, which are the planes for the 4 parts that all share that common reference. So I have guaranteed objects centered on the right plane, and I have 1 mates instead of 4, and it's all using plane mates. So unless I delete the part, this mate will never, ever, ever fail. Like ever, right? So that's superior to me than trying to mate these edges up, because those edges can change, those edges can fail, or those faces, edge of the sheet metal. I got to be careful because like this is an edge in SolidWorks, right? So we'll show those components again. Right, so I've got some that looks like this, and of the number of parts that I have, again, remember, usually you have 3 mates per part. So if I go to evaluate and performance, I have 373 components here. Wait, what was top level? Number of top level components, 146. So at 3 mates per component, I should have roughly 450 mates. To lock down every component, XYZ, 3 mates per. But with patterns, with MultiMates, with a few other things, I've only got, I don't know how many that is, that's probably 2 dozen. Looks like I've got 4 dozen mates. So, roughly 50 mates instead of 450. Using, and I didn't count the MultiMates, because those aren't a 1-to-1 scale. Using patterns and references and features and all that kind of stuff. All right, we got that. Okay, any questions on anything we talked about so far? Wow, this class is going better. Going faster, I should say. Yeah, so clearly, we'll use this example here. So clearly this is a subassembly, right? Because I use this like 4 times in the design. And I've just duplicated, you can show kinematic motion, or you can just duplicate the objects. So in this particular instance, I said, here's where it is extended and here's where it is retracted, because I didn't have to show the kinematic motion. And showing the kinematic motion is more work, or configuring it and flipping through them. So I just have constant design feedback. So I just have 2 of these in my design, and one of them is excluded from bill of material. So I visually see 2 objects in my design. And in this context, it was deemed acceptable. Depends on the contractor, design, or the environment. I'm not saying this is an always right thing to do. In this instance, it worked well. And so I made a common subassembly, which is this. So that one, that one, that one, that one. Right? All of those are identical. This one had a slightly different block on it, so that's its own subassembly.
You talk about readability. How would I know, as an outsider looking at that, was it built that way, that you have 2 instances of that in there?
Well, and that's a very good question. In this particular instance, I was a sole designer, and unless I died, nobody was ever going to touch it.
Okay.
And so it's what made sense to me, and my preeminent concern was not giving it to somebody else.
So this example would not be good readability.
It would not be good readability in a team that had different thought processes. If I was going to do it, what I would do is the exact same thing, and then before I was ready to release it for manufacturing, I would go through and delete everything after I've proven the design. There's a lot of things I'll put in or not put in, And then once the design is proven, so like fillets. Fillets should always be at the very bottom of your feature tree. Unless there's a compelling reason to otherwise, fillets are at the bottom. Lots of reasons why, but predominantly because fillets are performance killers, largely aesthetic, and only necessary 3 seconds before you hit the order button. So I'll do an entire design and there's not a fillet on it, which is kind of annoying because I'll get 3 people to come over and look at my design, and all 3 people will say, you need to put a fillet on there because someone's going to walk by and rip their shoulder open and then there's going to be blood everywhere. I'm like, yes, I know. Does the machine do what you want it to do, right? But fillets at the very bottom, and most of my designs will honor that. Sometimes you have to do a fillet higher so you can linear pattern it or a few other things. But in this particular instance, you just fillet everything. Here it's because of laser. Your laser costs less and you get a better part if you have fillets. Lasers hate hard corners. They hate them. There's a large manufacturing explanation for that. But in this instance, I just do my whole design. It's done. We do the design review, talk to the customer. Everybody likes it. And I spend like 3 hours adding fillets to every imaginable part. And then I hit the go button and we build the machine. I don't know how I got in the fillet tangent, but we're off of it now. Okay, so we've got to design a few other things. I knew we had access problems, so we slotted out everything so I can now loosen these bolts and adjust my cylinders all without taking the machine apart. Big, generous clearance holes when and where able to be able to put hoses and wires and access these different things. So even in the design, we're trying to limit our liability and maximize our productivity in the SolidWorks environment, but it also transcends into the machine design environment or the product design, whatever you're designing, and thinking beyond CAD. Right? I fillet all of my sheet metal parts all of the time because beyond CAD, I get a better part made. It's better, it's less expensive, it's cleaner, it's radiused. I would rather pay a laser to make a radius than a guy with a grinder, right? So to limit our liability is more than just myself when I'm designing, when a change comes, when my boss can't make up his mind, and when I click that button, what's going to blow up and how do I optimize that? But it's what do we do in manufacturing of the individual pieces? In this particular context, what are we going to do with assembly? And beyond that, what are we going to do with maintenance? Right? Everything we design is maintained in some capacity. So I might be able to assemble this just fine and it'll work, and then something goes wrong and I didn't maintain it. Do I have to disassemble half of the entire machine? Or am I going to be able to walk into a factory, talk to the maintenance guy who worked on my equipment, and not have him curse at me? Right? That should be everybody's end goal in this particular context of equipment design. I've been on both sides. I've gotten hugs and I've gotten cursing at. So depends on the day and it depends a lot on the maintenance guy. All right. Any questions on any of that? The main thing I'm trying to convey, though, is think ahead. Right? A lot of designers I work with, they look at a table and like, well, I need a sketch. So they start a sketch on the right plane because that was the closest to their mouse. And they draw a rectangle from the bottom left-hand corner of the origin out and they throw 2 dimensions on it. Right? We want to think ahead. When I take that tabletop and put it in my assembly, is it going to be in the position or am I going to have to rotate it and try to figure all that crap out? Right? If my origin's in the middle and I go put my holes in there, am I going to have a reliable point that I can mirror about? Or do I have to create a bunch of other geometry and then more hack apart my model to try to get my holes to mirror over the center origin of my 3D design? All the way to manufacturing, all the way to assembly, and all the way even to maintenance, right? Maintenance is the very end of your thought process, because after maintenance, it just gets scrapped, right? You maintain it for a point, and then you just throw the machine away. Like who's ever been to the JCI Boneyard, right? That's where, in this context, that's where all of your machines go. Somebody laughing in the background, I appreciate that. I'm not the only one. All right, I got one more example here. We might talk more about the table, or do some more design. Oh, one thing I was going to talk about sketching. Who's familiar with 3D sketching? Right? It's pretty awesome. 3D sketching is fantastic. I'm going to not let you see my screen because I don't remember if I set this up right, and I want to do a shock and awe. See if, oh, okay, I did set it up right. Perfect. Okay. Perfect.
Oh,
Oh no, we're not there yet. So this is standard. This is standard 80-20 Guardian. Okay. I'm sure everybody in machine design has done 80-20 Guardian. We all understand what it is. Extruded aluminum. It's fantastic. Everybody loves it, except for maintenance people. And so part of the challenge, part of the rub of 80-20 Guardian is the holes. Right? I can give somebody a nice print, but I need these stinking little holes everywhere so that I can tap the end and then put my 5/16 button head cap or button head. What he said, so I can tighten this down, right? Because I get the little button head to sit in this groove, and the button head fits in the groove, and I put my Allen wrench down. It's fantastic. How do you put all those holes in there?
With a bureau.
Okay, in CAD.
With a hole wizard.
With a hole wizard. Perfect. All right. So how many hole wizard features do I have to put these holes in there? And not Rick, because he's being too smart. Who wants to take a guess?
how many what?
How many hole wizard features have I used to put all the holes in this Guardian? 2? 1? Okay. So for those of you that don't know, you can do 3D hole wizard features. So all of these points, I basically said, we'll delete this one, right? So I basically said points, put it on that face, select other, pick that edge, and make that concentric. So now when we build, there's a point on that face that's going to blow a hole through that tube, or extrusion. And now when I go to make a detail print, I get a cut list that's specific per geometric object of, or geometric body uniqueness. And I can make a print and say, cut this 12 inches long, and then put a hole here, here, and here. And I think I set that example up. Maybe. Oh, buddy. I suppose we could, so I was almost done with the example. I want to show you guys how to do the ordinate dimension. There you go. So we're going to cut something 42 inches long, and at 16.875 and 35.25, we're going to drop 2 holes in it. So from a sketching standpoint, I have a single hole wizard. They're all tied to the same feature. They're all the same diameter. I can put any hole anywhere I want inside this frame, and I can make a print and detail out every single one with minimal effort, versus letting the guys on the floor try to figure it out, which happens. I mean, some shops go either way. Like, the guys can figure it out fast enough. They're really good at it. Okay, fine, whatever. It's all about what makes money. Any questions on any of that so far?
Can you review how you made that point between the intersection of those two 80-20s again?
Yes.
You did that kind of quick, and
I did do it kind of quick. So in a 3D hole wizard, whatever face you hover over, it'll put a point there that's on that face. So all I did was I put a point on this face because I need a hole through this tube that lines up with this one. And there's a select other command that I can make the face disappear. I can pick on that edge and then grab this and make it concentric. So it's on this face, concentric with that. This is why I hate micro clicks. But yeah, so you pick the edge, the face doesn't work. You pick that point and make it concentric. So now, if I look at my 3D sketch that's powering my weldment structural member, wait for it, and I say this is now going to be 5, that tube moves, and that hole moves.
How'd you populate that hole at all the joints, though?
In a 3D sketch. If you haven't played with 3D sketching yet, it's just magical.
Okay.
We'll leave it at that.
So have you used hole wizard before? I just regular 2D surface.
Yeah.
Okay.
If that's basically giving you that first pick that you did on a surface. With your regular hole wizard, when you're on a surface, it gives you that surface to start on. It gives it to a couple dimensions.
Here, I'll
sketches it. You don't have a face to start. So.
I'll make it more simple. I'll make it more simple here. Let's say this is not recommended. It's not best practice. 3D hole wizard is rare in practical form, except for what I just showed you. But I could, in the 3D hole wizard, you can in theory do this all with one feature. You shouldn't, and that's bad, but you can do that. And I'm just doing that same thing in a proper form in the weldment, or in the weldment tools, but in the 80-20 structural guarding, to minimize my liability, reduce it to one feature, and very, very, very quickly accomplish all that. Yes?
So the very first thing we did, we drew our component with our origin at center mass.
Yep.
And you mated that. You didn't fix it.
Right. Fixing is bad.
Can you go back and do that again?
Yep. So we'll actually do that in our. I was going to get back to our table example. So back to session 1. We drew all this in session 1. So our table leg here, I insert into the assembly and it's automatically fixed. I don't like that. So we're going to right click and float. So now this can move around.
Okay.
So I'm now going to grab the origin of my assembly.
You right clicked on the property menu?
I'll just right click on the component itself, and then it says fix now, but if it's fixed it says float, it's float, it says fix. So I'm going to, yep. That's the most fun way to blow up somebody else's configured assembly. Find a random part, fix in all configurations. So we're going to pick these two origins. So these, right? So each origin is surrounded by 3 planes: top, front, right. And so we'll pick these two, and we'll say mate, coincident, align axes, and green check. So now I have one single mate that's going to put this exactly in the center of the origin, instead of it fixed in arbitrary space. We don't like the little F, the fix symbol, and we don't like the minus symbol, which means it can now move around. This can still move. So I have to add mates to constrain this, and when this no longer has that minus symbol, then I'm done adding mates. Because I'm going to add legs. Yes?
Because I'm that slow, you picked origin, and then what was the mate?
Yep, so origin, coincident, align axes.
Okay.
So it's origin, coincident, align axes. So this, I'm just going to mate top of that bot to there. But now I've still got my XY problem. So I'm going to, on my front plane, we're going to mate, make a multi-mate, expand my tree, and pick front. On my right plane, my common reference should always be my origin planes when possible. Right to right, create multi-mate folder, green check. And so now I'll go through here and I'll rename this to front mates, right mates. I usually make them the why won't that drag? Usually make them up top so I can find them. Now these multi-mates only have one mate, so why would I do this? Why would I go through that extra work, name them, organize them, when it's just one mate? So you can add more. I'm going to still add legs. I'm still going to add the plastic beauty ring and the bushings and the cap and a whole bunch of other random stuff, right? So I want to think ahead and say, when I'm constructing my assembly, what else am I going to add? Is it going to be designed properly along center origin with mate alignments or plane alignments? And I can edit my front mate at any time and then add that other constraint, minimizing my mates, in maintaining my performance, and minimizing my liability as I continue through my design. So it's not best practice to just always create 3 and always do it, because I'm probably never going to mate anything else at the top, right? So think ahead through the design, understand what we're constraining to. I'm leveraging those, which I'm going to put other things on, and so it's worthwhile.
So, playing devil advocate here.
Yep.
Why would the great minds at SolidWorks fix that first object? There must be some logic to that.
There's not. I have personally spoken to the CEO of SolidWorks and complained to him about that and about 3 dozen other things. That might be why he doesn't take me seriously. And he says that that's the way it's been from the beginning. Nobody really complains. It works for most people. Yeah, maybe in some instances it's not the best, but his point was, if they don't fix it, and as you start mating things together, you have this whole blob that's moving around, which is much, much worse then one thing fixed. So he considers it an advanced feature or an advanced functionality where if you understand all the implications, it's better to float it and constrain it intelligently. But for the, we'll say 70% of the people who don't do that, SolidWorks fixing it prevents huge performance problems and huge other problems, cuts down their tech support problems, et cetera, et cetera. So they're taking, SolidWorks is programmed to the lowest common denominator, and their default action in most instances is better than not that default action.
But you just replace the fixed with one single beat before you constrain it. So
Right. So it's not a ton of work. I would personally love a system option, right? Like, I know what I'm doing. Uncheck the box. That would be awesome. And I'd love to have, like, uncheck, don't fix, and another check, create my one mate.
Doesn't it only fix it if you check the green check mark?
No.
Oh.
No, so if I take this and I put it in an assembly, so here's the difference. If I click on the green checkbox, it'll put it exactly on the origin. And that's the other argument is that, well, it's, if I do that, then it's on the origin, and then you have no argument. And I'm like, really? How many people do that? In like a company, I've never found everybody do that consistently. So now you have inconsistency in it. Now I'm going to assume because it's fixed, it's on the origin, and it's not. And I'm going to mirror my plane, and I'm going to make a $50,000 machine wrong because it's off by a quarter of an inch.
So
Because
it's always fixed. It's just fixed to the origin if you do the green check mark.
because if I
You always hit the green check
right
mark.
because if I click in random space, it's fixed. Everybody assumes it's in the origin, and I mirror about my plane, and it's wrong. So again, to limit my liability, we can't assume. Because everybody knows what assume is, or does, or
So if you do the green check mark, what point on the component is it fixing to the origin?
nothing is fixed to the origin. It's fixed in random space,
Oh.
like this.
I thought you just said the green check mark fixes it to the origin.
It places it on the origin and fixes it. It puts it in geometric space. It does not constrain anything.
Not coinciding.
So it's like this. I can rotate this in random space, right-click, fix. This is now fixed. It does not move, but it's in total random space. If you click the green checkbox, it just happens to be in total random space on the origin.
But no particular point on the origin, just wherever it landed.
Well, it aligns the origins.
Oh, okay.
Origin,
Yep.
part, the origin, and
Okay.
the assembly.
We'll see if I think I used a big assembly, so it didn't give me a.
If you don't have
preview.
the first plane, your normal plane, what it would be, then the whole thing is going to be spun around somewhere. And
So
then you
yep.
say, okay, I'm going normal to this
Flips
face.
Yep. So like here, no matter wherever I click, it's going to place it randomly there. If I hover over my origin, it snaps to my origin. Or if I hover over my green check, it snaps to my origin. So it's just going to geometrically go there, but it's fixed in arbitrary space. As from a reliable assumption standpoint. All right.
How that can really get you in trouble is you have parts that somebody created from something that's on a compound angle.
That's good times. That's when I walk into a company and they're like, "We're having problems. We can't figure it out." And it takes me 10 minutes to figure it out. I'm like, "All right, guys, this is what you did." All right. External relationships. We've got, I don't know how much time. 8 minutes. Do we have more questions? Anything else we want to talk about, or do we want to get into external relationships? Because I think that's my last slide. Who does external relationships? Oh boy.
External relationships, huh?
Like in context design, top down design. The little
Saving the
arrow
part
and the
externally?
carrot. The what?
Like saving the part externally?
No, I'll show you. Ah, crap. And this other example is going to take a long time to open. Maybe not. We'll see. Yeah, but I have a cool example to pull up. Okay. So I'll talk about it theoretic. So if I put this on the tabletop, I could constrain the holes in the tabletop parts to the holes in my legs. And if my legs move, the tabletop holes will move with it. So in the PowerPoint, we say when it is allowed, or this is allowed when you're in a project-based design, external relationships can save substantial time if used correctly. You have to understand how they work. It is possible to use circular references, which are really fun. You hit rebuild and your part gets bigger. You hit rebuild, it gets bigger. You hit rebuild, it gets bigger. You hit rebuild, it gets bigger. Because it's self-referencing, it just keeps growing. That's exciting. If you build them in a robust way, which we'll talk about. Be conscious of making small changes. So this is one of the things that I see burns people the most. They have a 300 part assembly. They make a minor change. Via external relationships, 7 parts get changed. They think they only changed the one part, so they rev the one part. Here's on the print rev A. Here's rev B. I move that hole. They make the rev B change. It doesn't fit the 7 other parts because SolidWorks shifted that hole in everything. And that's a simple example, but it happens, and when that happens, that really bites because it's hard to figure out what happened. Speaking from experience, I've been that guy. When it is not allowed in product-based design. So projects is everything I've showed you so far. Customer says, here's a project. We need a machine to do this. Those parts have never been designed before, will never be designed again. They're used nowhere else. They're in that one folder. I give that one folder to the customer. That's end of story. You can use external relationships very safely because it's a project and it's constrained inside of that. And a product, if I try to use external references for this tabletop, and then I put this table in a different assembly, well, those holes are constrained in my first assembly. So now my second assembly has to open my first assembly to figure out where the holes are in the second assembly. And you get a lot of problems really quickly. So external relationships, except for insert part, and there's a few other exceptions. Need an assembly to build the geometry. Using a part in an assembly that didn't constrain the geometry requires other assemblies to be opened, degrading performance and creating a spider web of relations. That can't be overstated. And then also when it's not allowed as standard libraries, and this is pretty obvious. If I have one part that I want to use 30 places, I can't say this one part has a hole based on this one assembly, because when I use that part in 30 places, I have to open that assembly all 30 times. Because you're developing that constraint and that relationship. So here's a great example. This plate's, the only dimensions in this plate are those 3. 37 1/4 by 18 by half. I think those 3. Every single one of these holes, 0 dimensions, no constraints. We only have these funny little relations that say someone somewhere else somehow is telling me where I should go. And the reason this is awesome is because other than fillets, you put in holes last. So I designed, I don't remember which one's mirrored. Okay, so here, the right, yep. So I designed all of these on the right hand, and this is a mirrored part, mirrored automotive part. So all of these parts I designed on the right hand side, and then I mirrored them over to the left, and every hole in this plate, so these holes here are all tied to, oh, that was a mistake. Let's do it this way. So every single one of these holes is tied to the tapped hole in my mating part. So if I take my entire assembly and move it over to 1 inch, everything moves. And I'll demonstrate that, although this is a performance killing animal. So we might just watch the screen and think for a while. And I gotta find my mate. Please hold. That's the distance up. It'd be a distance. I could have probably prepared this part better. Oh, and here's another mate, or here's another pattern. I got these 3 tooling balls, right? Just pseudo random pattern. I put one of those tooling balls in, and then I said the other 2 are wherever the holes are. And if I add another hole, I get another tooling ball. It's really cool. And should have figured this out beforehand because I'm not. Oh, there's my mate. Okay, so here's my mate to the edge, 7.5 inches, and I declare it to be 7 inches. And it's now thinking. There's my CPU going. All right, so we got a cool black screen with a fun CPU meter. It's now moving those and rebuilding everything. And as annoying as it is to wait for SolidWorks, it's a lot longer to do it manually. I optimize a lot of designs where you can click on a few buttons and SolidWorks thinks for 3 minutes and you get 3 days worth of work done. And a lot of my customers will complain, they're like, SolidWorks takes 5 minutes to think about it. I'm like, yeah, and it took you 3 days before. Like,
Yeah.
let it think. Anyway, so we moved it a ½ inch over to the right. Every single hole lines up. It'd be really embarrassing if they didn't, but it looks like they are. And to limit my liability, I only did external references on half of the design, center, origin design, and I mirrored all the holes. Because every single time I say this hole belongs to this part in this assembly, that part could change, that assembly could change, something could blow up, and I may have to fix every one of those holes, legitimately or illegitimately, right? I give the design over to Bob, and Bob blows it up and gives it back to me, and I don't know what happened, I gotta fix it. I mean, or I could have changed something legitimately, or a lot of things could happen, right? But I only ever wanna fix half of my holes. So just like we did in the tabletop, I don't want to dimension them. In this context, I don't want to do external relations. So I just drew a vertical center line, mirrored everything over, and now have perfect hole patterns on both sides that are a straight mirror on this particular part with minimal liability. And then I also mirrored several of my components. So all of these components here also work on the other side. So there's my preview. I don't have to do any mates, and we can see the holes automatically line up. I mirrored the holes and mirrored the components, and if everything is set up right and works properly, everything will line up. I am out of time.
So your cylinders on the left side are mirrored to the right side.
Yes, sir.
So now you have right hand and left hand cylinder.
So they are the same geometric shape, they're just mirrored over the origin as a different geometric placement. But they're the same, they're the identical part.
So your air fittings would be on the other side.
So my air fittings are on the left side here, and my air fittings are on the left side here. So it's the same thing, it's just moved over. So SolidWorks has options for this. So here's the purple highlight. SolidWorks gives you 4 options. The first option is flip it. Second option is just move it over. The third option is flip it over, and the fourth option is flip it the other way. So as long as you pick the right option, you can take something and just move it over and maintain its orientation, or flip its orientation, any one of the ways. And you can do that via the bounding box or via the center of mass. So you can get a different result between these two options. It's all options based, right? There's a button for everything. Almost everything. You just gotta know what buttons to pick. So, I am out of time. I'll be around here a little bit, and we're gonna run up, and there's prizes and more food and giveaways and stuff and whatever. If you have any questions, let me know. The presentation should be available online in a week or so or something.
Thanks, Andrew.
Yep.